All right, we can use KSP to predict if a precipitate will form. So are there enough ions present or enough moles of each material? So that's your first thing that you determine in a problem. And then you're going to calculate molarity based on the total volume of the solution. So if you're mixing two, you're going to add them. And then you're going to find the concentration of each ion, assuming complete ionization. So that would be the maximum number of ions present. And then you are going to determine what compounds are formed by the reaction of available ions. So again, precipitation reactions are usually double replacement reactions. And then you are going to calculate the reaction quotient and compare it to the KSP of the predicted precipitate. And then same as what we had before, you compare the Q value to the K value and determine out which side of the equilibrium you are on. So we're going to do a sample problem here. So I'm starting with 100 mils of 0.0075 molar sodium sulfate. And I'm not going to convert this to liters. So I'm going to use something called millimoles. So this will give me 0.075 millimoles. So basically the liter part is going to cancel, and we're just going to take the milli part from the milliliters and the mole part of sodium sulfate. And this just saves you a step. You'll see what happens with the milliliters in a minute here. I have 50 milliliters of 0.015 molar barium chloride. And then to do my molarities, I'm going to take 0.075 millimoles over, adding these two together, 150 milliliters. And you'll see your milli cancels and you're back to moles per liter. So for the sodium sulfate, that is going to be 5.0 times 10 to the negative fourth molar. And for the barium chloride, we're going to do 0.75 millimoles over the 150 milliliters. And that's going to give me 5.0 times 10 to the negative third molarity. So when I react these two, sodium sulfate and barium chloride, I'm going to get NaCl and barium sulfate. So sodium compounds are always soluble, so this is going to be your precipitate. So I have 5.0 times 10 to the negative fourth and 5.0 times 10 to the negative third. So if I write my equation for the KSP expression for barium sulfate, it's going to ionize or dissociate into those ions. And then for sulfate, this is going to be my concentration, and for barium, this is going to be my concentration. So I'm going to write my KSP expression. And I'm going to use the 5.0 times 10 to the negative third molar and the 5.0 times 10 to the negative fourth molar. And this is going to give me, okay, I can do this without a calculator, 25 times 10, add my exponents, negative 7. So I need to make this smaller, so my exponent's going to go larger. So that's my KSP, or my Q value, sorry. So then I'm comparing these two. So if I look at, always put Q in front. And then I'm going to compare how that relates to 1.1 times 10 to the negative 10th. So this one is greater than KSP, so a precipitate will form. So it's going to try and get these ion concentrations down so they equal this for equilibrium.